Welcome back, students. Let us now begin section 7.2. Here in this section, we are going to introduce a set of new trigonometric identities, which we call the sum and difference identities, or equivalently speaking, addition and subtraction formulas. It doesn't matter which name you use. What really matters is to use it accurately. Here's the first formula. Sine of alpha plus beta equals to sine of alpha cosine of beta plus cosine of alpha times sine of beta. Next, cosine of alpha plus beta equals to cosine of alpha cosine of beta minus sine of alpha times sine of beta. And these two are the standard sum and difference identities. These two are actually very, very difficult to prove, so I'm not going to attempt it in this video. What I'm going to do is to prove it in a separate video. Yes, I will prove it in front of you, and probably make it into an optional video because it goes pretty deep. But the other formulae are all deduced from these standard two. And for example, here's a prime example. Tangent of alpha plus beta equals to tangent of alpha plus tangent of beta over 1 minus tangent of alpha times tangent of beta. How do we prove this? Well, here's a proof actually. We begin from the quotient identity. Let's improve the font a little bit so that you can see this thing better. Here's the strategy. Tangent of alpha plus beta is equal to sine of alpha plus beta over cosine of alpha plus beta. You can easily see that because tangent is sine over cosine. And sine of alpha plus beta and cosine of alpha plus beta are right over here. The standard sum identities for sine and cosine. So what do we have? We have this over that. And then what we are going to do next is to simplify by dividing each term by cosine of alpha times cosine of beta. That's what we're going to do. Divide each term by cosine of alpha times cosine of beta. By the way, let's recap what we did. Tangent is sine over cosine, yes, and sine is here, and cosine is here. So rewrite those into fraction form to get this. And what we are going to do now is to simplify by dividing each term by cosine of alpha times cosine of beta. Okay, let's go ahead and do that. Dividing each term by cosine of alpha times cosine of beta. If I do that, then what happens to the first term? Cosine of beta will be divided out, and the sine of alpha divided by cosine of alpha, that's going to be tangent. Now let's move on to the second term. Again, let me remind you, we are dividing each term by cosine of alpha times cosine of beta. So this cosine of alpha will be divided out, and the sine of beta divided by cosine of beta is tangent. How about the third term? Cosine of alpha times cosine of beta divided by itself. So we have just one. Finally, sine of alpha times sine of beta divided by cosine of alpha times cosine of beta. So what do we get? Sine over cosine, that's tangent. And this one again, sine over cosine, you're going to get tangent. And isn't that what we wanted to prove all along? Yes, indeed. Let's go over to another example. This time, let's work out the difference identities. How about sine of alpha minus beta and cosine of alpha minus beta? Well, actually here they are. Sine of alpha minus beta is sine of alpha cosine of beta minus cosine of alpha sine of beta, etc. And let's compare this with the original. We have this alpha plus beta, and we have this alpha minus beta. And consequently, this plus sign was changed to this minus sign accordingly. How about cosine case? We have cosine alpha plus beta, and that's changed to alpha minus beta. We have sign change. And accordingly, what do we have here? This minus became now plus. Looks like something is going on here. We have some definite pattern. Can we prove it? Oh yes, indeed, it's not difficult. All you have to do is to recognize that cosine or sine of alpha minus beta is the same as alpha plus of negative beta. And then we can apply the original formula. Here we have beta and then beta, and these will be replaced by negative beta and negative beta. And let us make this observation. Cosine of negative beta is the same as cosine of beta because cosine is an even function. Sine of negative beta is equal to negative of sine of beta because sine is an odd function. So we have the sign change as expected. How about the cosine formula? Pretty much the same. Replace beta by negative beta, and we result in same observation. Cosine of negative beta is the same as cosine of beta, and sine of negative beta is negative of sine of beta. So that extra negative collides with the existing negative, and we have the sign change. We have plus sign there, as expected. So there goes the proof. How about the difference identity for tangent? It's the same deal. Tangent of alpha plus tangent of negative beta in numerator. Consequently, we have tangent of alpha minus tangent of beta because tangent is an odd function. Denominator can be manipulated pretty much the same way. In short, we've been using these two identities, this one and that one, to prove other formulae. We use those to prove the tangent case. We use those to prove alpha minus beta case. One more? Okay, let's do just one more. Here's something called double angle identity. In a special case where alpha and beta are both equal to theta. They're all both equal to theta. So what do you get? Instead of sine of alpha plus beta, you get sine of theta plus theta because these two angles are the same. Consequently, from the addition formula for sine, what do you get? We have sine of theta, cosine of theta plus cosine of theta times sine of theta. Addition and multiplication are commutative, so we have twice of sine of theta, cosine of theta. And there goes the double angle identity of sine. How about the double angle identity for cosine? It's similar. Just apply alpha and beta equal to theta into, well, this. And then what do you get? Cosine of theta plus theta. We have cosine theta times cosine theta minus sine of theta times sine of theta. We have cosine squared minus sine squared. It'll turn out that these two double angle formulae, especially the second one, are very important. Especially the second one is really important. But for now, let's postpone double angle identities and their applications to section 7.3 topic, and let's just move into applications of sum and difference identities. Let's begin with an elementary example like this. Calculating trig value sine of 5 pi over 12. Now, please note that 5 pi over 12 is not a standard basic angle. And here is a trig diagram that shows all the basic angles. We have 0, we have pi over 6, pi over 4, pi over 3, pi over 2, and so on and so forth. X coordinates, the first coordinates are cosines, and second coordinates are the sines, and tangent will be y over x. Now let's go back to the problem. Sine of 5 pi over 12. 5 pi over 12 does not appear in the trig table. So how do you find out the precise value without using calculator? Well, this is how. You can decompose 5 pi over 12 into 2 pi over 12 plus 3 pi over 12. This decomposition is not unique. So this may be one way to handle, or another way to handle it may be, well, there may be something else. In this case, 2 pi over 12 is same as pi over 6, and that's a basic angle. And 3 pi over 12 is pi over 4. That's a basic angle too. So what do we get? Sine of alpha plus beta forms. So we have the addition formula for the sine, and then let's just plug in all those values. Sine of pi over 6, cosine of pi over 4, and so on. They're all basic angles. Consequently, we can use this trig value circle. And as a result, we have this kind of answer. Square root of 2 plus square root of 6 over 4. It'll turn out this kind of numbers are very, very typical. How about the next problem? Cosine of pi over 12. Well, here it is. Cosine of pi over 12 can be rewritten as cosine of 3 pi over 12 minus 2 pi over 12. And that decomposition is not unique, for example. It is possible to use this kind of decomposition. Pi over 12 is, let's see, 4 pi over 12 minus 3 pi over 12, which is equivalent to pi over 3 minus pi over 4. Yes, this will work too, because we have the same number as we wanted, and we have a difference of basic angles. But what I did here is, of course, another decomposition, pi over 4 minus pi over 6. This one works out too. And because these two angles are basic angles, just apply the trig diagram like this for cosine of pi over 4, cosine of pi over 6, sine of pi over 4, sine of pi over 6, and so on, and plug in all those numbers. And what we get? We have, well, this value. Well, turned out that this value and that value are the same, and that should not be surprising, to tell the truth, because if you add up these two values, 5 pi over 12 and the pi over 12, you get 6 pi over 12, which is equivalent to pi over 2. So these two angles are, as a matter of fact, complementary angles. So sine and cosine values will flip-flop, and that's what you're looking at. But in any case, these numbers are going to be very typical. You're going to get something like square root of 6 minus square root of 2 over 4, or square root of 2 minus square root of 6 over 4, things like those. But in any case, if you have denominator 12, if you use those if you use those addition formula for sine and cosine, it is typical that you end up with 4 square root of 6 square root of 2, one way or the other. Of course, if you use tangent, things will be different, like this problem. How? Well, here it is. Tangent of negative 7 pi over 12. The decomposition is not unique, but this is the way I did. 2 pi over 12 minus 9 pi over 12, and they are both basic angles. Pi over 6 minus 3 pi over 4. And consequently, you can go back to that trig diagram and plug in all those values according to the sum formula for tangent. And if you do, then you get something like this. Simplifying, you're going to get this value. And finally, if you rationalize the denominator, you're going to get something like that. The final step of rationalizing the denominator is kind of like this. This is the same as, as a matter of fact, I should have done like this. Same as multiplying the conjugate of the denominator. Change this to plus, and change that to plus, and fold it out. If you do that, the denominator will become rational. Why? Because we have a minus b times a plus b form. So denominator will be square root of 3 squared minus 1 squared, or 3 minus 1. And the numerator will be a bit more complicated. But in the end, if you do some simplification, you're going to end up with something like this. The detail is left to the students. After all, this was well covered in college algebra or intermediate algebra.